we started so late, and if anyone wants to walk out, you can. I used to have a family as well. I never stayed half an hour past the but what I'm saying is, for the ending, is most aircraft programs that I've worked on have been for external carriage. I know what's for external carriage. It's no big deal. Internal carriage, you actually have separation problems because I'm not sure how we can do that. And I actually want to describe the issues that I feel that are facing us right now. By the way, this is not a desirable configuration. We do not want bombs hitting each other and exploding next to the aircraft. So, I've been doing, so this was done back in, I believe, back in the 90s. What happened was the Air Force, the U.S. Air Force, Australia, and the Navy combined to do bomb bay testing for the F-111. What they did is did a wind tunnel test for a small smart bomb, or basically a small bomb. They did it in the AEDC 4-foot tunnel at a 28 scale, model scale of the F-111. The problem was it had a sting. It could not get into the bomb bay for the F-12 part of the bomb bay. So the Australian Air Force did 16 flights. All the flights were released from the forward bomb bay, but he actually got the sting into the bomb bay with reasonable match with the flight test data. All the stores from the aft bay, we didn't get a match. So what was the problem? So we did a C of D calculation. There was a TTCP, that's called the Technical Cooperative Program. So there's a cooperative program between Australia, Canada, U.S. Navy, and Great Britain. We did CFD calculations for the cavity, and we showed that if you use CFD for inside the bomb bay, then the pitching and yawing moment changed as you went into the bomb bay. So we're able to, we didn't match the flight test data. One of the problems with the flight test data was the instrumentation wasn't accurate enough where we could say, oh, we've got a good match. Well, what we did is we showed that at least the stars were pitching in the correct direction, as it was. And the most important thing we got out of that is we decided how we should do testing for bomb bays for the P8 as well as the JSF program. And the P8 is just and the P8 is just a 737, and then most of you must have flown because that's the main aircraft flying between here and Istanbul. So what they did is they put a bomb bay in a P8, and we tested with two types of screw. We tested it with a strut-mounted sting, so you could go all the way into the bomb bay, and we tested it with an aft-mounted sting. So here's actual wind tunnel test data. And that's normal for us. By the way, that's shown as DCN. That's the incremental normal force. You take the grid data, and whatever the free stream data is, you subtract that angle out from the data. So this is the actual grid data that we use. So that's the incremental normal force. And notice it seems like it goes to zero all the way at the end of the cavity. And the same thing happens with the incremental pitching moment. But the important thing is that this is the strut steam. that the strut was all the way inside the body. The spin and the out went all the way outside. So we merged the two sets of dust data to do our simulation. And Bowling actually did CFD calculation to see if we could do CFD beside the P8 bomb day. So, and one of the things we used the CFD for was, after the wind tunnel test ended, we decided we wanted to change it was the Mark 64, we wanted to replace that with a Mark 82. So it's a totally different store. So we're saying, all right, we have good data for one store. Can we use CFD to see if we can predict the CFD for the other store beside the top day, and then use our incremental grid data to separate the other store. So this is the actual CFD calculation. And we actually said we can do it for 2 stores inside the cavity, and or 1 store. And so we matched the CFD with the wind tunnel, used the 3 streams for the Mark 82, and I cleared the Mark 82 for flight testing, as opposed to the Mark 64, which is the one that was tested. And the flight test didn't occur until after I retired, but I'm sure if there had been any problems, we would have heard about it. So I believe you can do wind power testing for 1 store, and then use CFD increments for a very similar store. The only difference between the Mark 82 and Mark 64 is the tails. And it turned out that Mark 82 was better than the Mark 64. So it's very easy to say clear it to the other configuration. Well, as you mentioned, this is the overflow calculation that was done by, actually it was Boeing Douglas, as opposed to one Boeing Seattle, so the CFD, and it was using the overflow code. And again, excellent correlation, but is this going to work for other populations? One of the issues with this dog bay is that there's shallow or deep cavities. It's a fairly shallow cavity, so it's more a lot like a pylon than it is a deep cavity. And this shows an example of a deep cavity, and I had midshipmen working, not me, naval cadets at the U.S. Naval Academy. They would do, it was a trade-off, they would do free work for me, and I would send them conferences to present the results. So they would, what would usually happen is they would take a CFD class in their junior year. They would go to Maui for the HPC Center to train on how to use the Maui CFD code. All the computation was done with USM 3D. That was a program developed by Nino Frank. And they were trying to see how well they could match the wind tunnel data represented by this configuration. If anybody is looking for a thesis topic, the cavity geometry is more than wind tunnel data as well. All I can say is it didn't match the data for the deep cavity. So right now, the question is, was it the experience of the user? My attitude has always been that CFD is going to be useful for store separation, where a junior engineer, somebody just out of college, who goes out to use CFD, can do trajectory prediction. And I think we're at that state now for external stores. I don't know that we're at that state for internal weapons. Another project we did was, and again, the Snyder and Young, professor at the Naval Academy. So studying what happens, what's the difference between a store that has an aft state, which basically does not disturb the flow through, with a store that has a strut, which you're going into the wind tunnel with. And so the test data shown here is at 0 angle of attack. And notice if you go negative, and by the way, the cavity data, we did free stream, we had free stream cavity data. Outside of the cavity, we had free stream data for this score, and we noticed that for negative angles of attack, there wasn't that data. But for positive angles of attack, the pitching moment was badly compromised by positive angles of attack, and that is due to the strong shock wave that you have forming between the strut and the outbound of the storm. So we did the CFD. I'm sorry, I keep saying we. Naval Academy cadets did the CFD. Professor Green Don supervised them. Professor Don, Professor Don, he was actually at Naval Academy for a summer, and he got Naval Academy curriculum running, and what he did is he actually modeled this configuration and used temperature-sensitive paint to approximate what happens. So that is the shock you see forming as the Mach, it's a blow-down vent tunnel, but we're running at Mach, I believe it was around 9 tenths. And so that is what happens with Here's the CFD calculation. This was part of a PhD thesis at the University of New South Wales. So again, Professor Down used the true scientific method. You have your graduate students do the interesting calculations and present the results. So there's a PhD thesis, not just that shows the correlation, it actually shows a design where it says you can really minimize this interference if you design this thing properly. So you have certain parameters for the sting in terms of size and width. The length of the sting is predetermined by how far away you are from the storm. In other words, if you're confined in a small tunnel, then your strut has to be at a certain length. But what we use the same strut that we use for the P8 program. We said, okay, let's use that kind of a strut and see if we can minimize the interactions within the square tunnel and see what the pressures look like. So if anyone is interested in this work, I can email me, and I'll email Professor Don, who's now at the University of California, St. Louis Episcopal, and I'll ask him to share the work with you. Last topic is basically measurement techniques. I talked about the 6 degree of freedom applications to telemetry. So we put a unit, the unit weighs approximately 6 pounds. You usually put the measurement, there's a telemetry unit as well as a accelerometer. The accelerometer gives you 3 degrees of freedom in acceleration and 3 degrees of freedom for pitch yaw roll rate. And what I'm trying to say is, if I have accelerometer data, you can measure what the pitch yaw roll rate and relate those to the yawing, pitching, and rolling rate. So using the actual telemetry test data, I can back out what the aerodynamic coefficients are. So one of the questions is, what happens with Mach number in terms of your ejectors? So I show 2 ejectors. So this is actual raw test data where I differentiate the telemetry, the pitch yaw and roll rates, PQ and R, to get the pitching, yawing, and rolling rate. The only important ones are really pitching and yawing rate, because rolling rolls for symmetric scores don't have that effect. So this is your change in pitching moment. Notice you have a huge change in pitching moment. The scale goes from 0 to minus 4. The reason you get that huge change is that's the effect of the ejector. The ejector is pushing the store in the nose and on the left part of the store. So this is exactly what happens in flight. So I'm knocking out the flight test data. So for the pitching moment, the first, in this case, it looks like 20 milliseconds. All you've got is the ejector. So the pitching moment is just a function of the ejectors. So not that you say, oh, we agree well with Z. You always will agree well with Z because first, the Z is really dependent on the ejection force. If you have the correct ejection force, then you will predict Z exactly. Now what happens if Z does not match your prediction? Any guess? What would you do? You've got a set of 10,000 that are clear flight. You don't have a $10,000 telemetry system, but your Z is different than what you predicted. You change your simulation. You go back and says, okay, I was using 2,000 newtons on the front piston and 1,000 for the back, and I'm getting a pitch that's different. So you just play games. So you play games. Don't play games with pitching limit. You play games with the ejector, and you match your displacement after 50 milliseconds. And so your displacement for the first 50 milliseconds is entirely due to the ejector. So don't ask me how are you going to model the ejectors. You model the ejectors with the flight. And if you don't have any flight test data, then you find somebody that has flight test data for the aircraft like the F-16 for the first, that has just Z versus R, and take the first 20, 30 milliseconds, and that will give you the ejectors. This curve is different for any massive store. So this is a function of the mass of the store. So your pitching moment is very easy to determine. Now, the problem with the yaw moment is you've got an awful lot of scatter in the flight path data. So that's just vibrations and things like that. So even telemetry, you get a lot of scatter and data. Now, I've done this since I retired, so I did not have naval cadets or students or people working for me to do the grunt work. So there's an elegant way of doing one of these computations, and I'm willing to send you the telemetry data, the telemetry data, so you can improve on this. But there's the crude way, where I just said, I'm just going to average the telemetry over 3 times. So when I average the telemetry over 3 times, this is the telemetry. So that is my calculated pitching moment. No, yaw moment, I'm sorry. So this is yaw moment. So I've got the yaw moment from flight test. Now notice, the yaw moment from flight test is 0 right at the initial time step. The reason for that is that the forward piston and the aft piston are pushing on the store. You design this store to pitch nose down. Exactly, I don't know exactly when it is, but it looks right around 20 milliseconds. The forward piston, the forward piston is no longer in contact with the store. The store is only in contact with the aft piston, which is still pushing the store away. So at 20 milliseconds, the ejectors keep the store from yawing for the first 20 milliseconds. Now, by the way, I used that in my simulation. When I got a yaw moment of 4, I said yaw moment doesn't really, or let's say in this case, the yaw moment was 1.4. I put in the yaw moment of 0 for the first 20 milliseconds because I know from previous tests that it takes around 20 milliseconds for the yaw moment to build up. Now, so this is the actual truth, but it's not truth because the data is crude. And here's the simulation. So This is my 6th degree of freedom program. Actually, I lied. I forgot. I just realized I should have put the simulation. Oh, I got another paper. I should have started the simulation at 0 for the first 1 millisecond, and then put in the yarn over. So I would have gotten this kind of a much better match. So anyway, I'm talking to myself. What it is that there is a very good match between the simulation I did before the flight test and the actual flight test result. So the result was that I got yaw and the Y position within 1 inch after about 400 milliseconds. And the reason for that is I had the correct thermodynamic coefficient as well as the correct ejective force. And I got that from the previous flight test result. Now, JSF, and again, this is the same concept as JSF. And what they show here is they're doing a simulation and they're showing the actual prediction versus test data. So that is about 50 milliseconds after the ejection. So that is quite good. What they do is they calculate the ejection forces using a structural dynamics model. So they don't even back out ejection forces from the previous one. We use an ejection force model that models the ejection, and they upgrade the model, improve the ejection using flight test data. And notice this is the actual telemetry data, and it looks the same as my telemetry data. Now, is there a way we could improve this? And remember, the JSF has both photogrammetrics and telemetry. It seems to me you have two solutions for the same trajectory. You could do, now this is why I say do the crude method. The correct way of doing it is to, right, I have that test data that's photogrammetrics and test data that's telemetry. There's only one true solution. If I do a least square fit for the two solutions, I will get the true, or at least a closer approximation of what the truth is. So, last topic I wanted to cover, and very quickly, it's sea air rescue. So sea air rescue is usually done by helicopters. And look at how to do that with the weapon. Yes. So I'm just looking how to do that. Is there any way we could do that using computational tools? So that is a trajectory simulation. I have no free stream air dynamics because we've never tested cylinders on the stock. I haven't done the aircraft aerodynamics. This is one application where I can see panel methods being useful. I can't see panel methods not used. Actually, I haven't used the panel method in about 30 years. I went back to this because panel methods are good at low speeds, and this you want to fly as slow as you can because the purpose is to drop something that hits the ground. So panel methods might give you at least an influence of the aircraft. And the stores, what I'd really like is I was interested in the decoy because the decoy is unstable. What I'm looking for is more and more calculation for cylinders and rectangles, because if you have a database of free stream and you have some influence for the aircraft, you can then say, let's see the flight test and see which one, just go back to the flight test, go back to the initial condition, see what you have to do to change to make a trajectory prediction. Because if that works, then you've got a process that works. So that's basically what I have to show. Just wanted to mention, just look at Moore's law. It follows. Back in 1967, or, well, the first time I did, let's say, CFD calculation, took 24 hours. Now that calculation in seconds. Now the state of New York, just light pieces. So CFD, if it keeps going at the same rate, we may be able to solve the Davis-Stokes equations in CFD. Don't know if that's the case. I'm not sure what to do with wind tunnels. I'm just trying to say, for cavities, maybe we should go to the drop test. Well, we know that the mass properties are incorrect, but we can do the drop test to get the aerodynamics and use CFD to validate, because we can put anything we want to in the CFD code. So maybe that's a way to do cavities. And that's working. The movie was working.
You have to click on it. Yeah. Not with that. Click it on.
Oh, okay. But, all right. This is the last problem. Notice when you drop stores, there's a dynamic interaction. You have to model that interaction, but that's easy to do because the dynamic interaction is fairly independent of the Mach number. And there's a paper. By the way, if any of you want me to send you anything, just send me a paper to tell me what part of the lecture you want me to explain. Because I have a paper that actually shows how you can use flight bus data to actually model the ejection characteristics during the drop. So, what I was actually going to ask for, but I guess that's a question to the audience as well as the panel, is do you have any ideas? What I'd like to do is improve the process of flight test measuring, because CFD, we know what it can do. Wind tunnel, we know what that can do. If we can improve the flight test, we can improve all the other. Now, if you ask for questions,
yes, you can.
Okay, so I guess we have 10 minutes.
Well, at this moment, we would like to open the whole session for discussion. You can ask anything to the microphone.
Yeah.
So, what do you want to ask? It's the platform is open to your questions and suggestions. But maybe, Alex, you can start with initiation to the discussion, as you have done in Rome. Remember, you were talking about photogrammetry and.
That's the question.
Yeah.
How do you? Okay.
Yeah.
Right. Yes, my question is, how do you do your flight testing? How do you measure, I guess, kernel, how do you know that you've done the flight test properly? Do you have cameras, chase plane? Okay. No, but see, my question is, how can we improve what we're doing? Improve, better, faster, cheaper. Well, actually, I forgot to mention one thing. The office had a suggestion. We have these collision warnings, like you back up the truck. Now, that must be really cheap. Wouldn't that work in terms of the store separation? That should be
Acoustic sensors, you know, just for the parking sensors, for the cars. Now they are becoming very, very cheap.
Because it seems to me that what I would do is I would put one in the nose. The office came up with the idea. If you put one in the nose, put one in the tail, and put one. I can tell you which part of the airplane is more sensitive. So you put three of those, and you'll have a much better prediction of the distance. Right now, the way I predict the distance is I have the CG of the store, I do my simulation, and then I have my computerized model, and based on the attitudes of the store, I figure out where the minimal point to contact is. Now, if we have acoustic sensors, it could be really cheap. I might get a better measurement, and then I could compare that with my CAD calculation. I said, okay, this is the nose that came closest to hitting the pylon or hitting the side of the fuel tank or anything like that. So that's something I never thought of. That's one reason I was anxious to utilize this series. Like I'd like to, I have all these ideas, but some of them don't make any sense. This might make some sense, and this might be something that would really improve the flight test process, because if you have a better...
Alex, can you please
sorry. Yes, okay. It would improve the flight test process because you would go back and say, okay, my CFD didn't work in this case. We have to fix it.
Information is very useful for one project. The issue is one project with Aselsan. Nowadays we are working on it about the contact of the weapons during separation. Slightly on ground test, and Aselsan is working on it, and I think it can be very useful, this information. But this the weapon we will deploy this weapon from a third and two weapon with time interval. The first weapon touching the other weapon during separation on ground test, and they will adjust its timing mechanism. We hope to finish it on ground test, and do according to the handbook 1763 ground test 1110. We need to be sure about no contact.
Okay. So I have a question back to you. So if you're doing a tear, why don't you change the release sequence, drop the bottom score first, and then you drop the outboard or the inboard, and you can't have any contact.
The first bone touching the second bone. The down shoulder.
Well, see, you'd have to send me a picture.
Or no. Okay.
Now, I think these acoustic sensors now are becoming very cheap and very precise, because the resolution were a big problem. They could not resolve below meter or centimeter. Now they are really very, very precise to avoid the collision of while you are parking, etc. And what is more, they are becoming really miniature, so you can put an array of them, you know, on the store or on the surface. I mean, you can really place an array of these, and you can really looking at the instead of audio signal, you can convert this audio signal to an electrical signal as well. That's possible.
Our intention is to solve this issue on ground test.
Yes.
But if we have some doubts, or if we want to be more sure about in the air launch, I think we can discuss using some extra instrumentation to measure.
Yes. Yes. Sorry.
I think Lieutenant Colonel Kurbaş explained our state of the art. We basically use the handbook 1763, and we use both telemetry data, like 60 degree of freedom sensors for the weapon separation, as well as we use photogrammetry. We are also improving on our CFD, I guess. But I'm always intrigued by the interface forces, you know, on the ejector. As you said, you can. Well, we did try to, you know, extract them, and we can do it to some extent. But as I commented yesterday, the variability of the pyrotechnic cartridges brings the variability of the energy released by the pyrotechnic cartridges brings some discrepancies to the process.
I actually contacted a friend in Australia. I worked with for 25 years. It used to be House First Operation in Australia. And my friend, who was the NATO representative for pyrotechnics, is retired in Philadelphia. They both gave me the same answer. The pyrotechnics, you have a crew at the Air Force or the Navy that actually is responsible for examining the pyrotechnics, and Colonel from here gave me the lifespan, so pyrotechnics last for 2 years. If the containers are open, they last for 16 years. If they've never been opened. I've never had a case where and over the last 50 years, there must have been hundreds and hundreds of flight tests that I either did the simulations for or people working for me did. I never had a case where the ejector variability came into question. In other words, you get the ejector characteristics which you first flight. Now, the variability comes in from your configuration. If you have the store being dropped from an outboard pylon as opposed to the inboard pylon, there's a huge variability in those. But the change with Mach number, no, it's a function of store mass. It's a function of aircraft loading. We fly the aircraft. So if you've got fully loaded aircraft with, I guess, carrying 10,000 pounds, as opposed to one store that's only 2,000 pounds, there's a huge difference in the ejector characteristics. But there is no difference from the flight at 8 times Mach number for the same configuration as it is at 1.2. Or the difference, there may be a difference, but it's less than I can predict. In other words, our measurement techniques can't pick up the difference in Z, and to do that by saying I can pick out, I have to match 1 inch and 1 degree for the first 20 feet of the trajectory. That is what I consider acceptable simulation. So pyrotechnics will give you a lot more than 1 inch or 1 degree. Photogrammetrics gives me that accuracy. Telemetry, 6-degree freedom telemetry that I integrate, I consider that not to be the truth. Now, for photogrammetrics, sometimes let's say, I say 1 inch. It's 1 inch after about 400 milliseconds. Sometimes within 1 inch, in the photogrammetrics will be 2 or 3 inches off after 400 milliseconds. So I do not believe that there is. I was underneath when you asked the question yesterday. I said, "Oh, I never thought about that. Maybe we have brand new pyrotechnics just because we're doing the initial flight test, and then when you go out into the fleet, that might be a real issue." But that's the problem. You have to have repeatability. You know, when I clear a store, and the closest I came was about 1.5 inches, and you relax the criteria to, in our case, when it's tip-to-tip impact. And because then you don't tip-to-tip in terms of missiles. So if you have the tip-to-tip contact, well, I never encountered that. I came within 1.5 inches, but this was in the case of Desert Storm, where they said, we want to drop the GBU-12. And anyone that's interested in write me Desert Storm GBU-12, we have to drop we have to do the clearance in 2 weeks, as opposed to 6 months preparation for the wind tunnel, or in those days, 6 months to a year to do a CFD grid or anything like that. We had the Air Force actually had the F-18 because they did ACFD Challenge 2, and they had a grid for the GBU-12. They did the simulations for me. They matched the previous Mach number. They did a prediction for the subsequent Mach number, and they were within 1 inch. My miss criteria was 3 inches. After the flight, it turned out to be 1.5, and we cleared it because there was an immediate requirement. Now, so that's probably the best use of CFD that I know of in the last 20 years, because you went directly from a CFD calculation to a flight clearance, not where we tested. We tested the endpoint, and we issued the clearance. But so the next day, they could actually go and drop the GBU-12s in Iraq. So I don't believe there's a pyrotechnic question, because with the pyrotechnics, 1 inch, the ejectors are really the driving force.
Thank you. I have another question regarding flutter testing for Dr.
No.
Actually, two questions. Two questions. One is, as we perform the actual flutter testing on the aircraft is burning up fuel, so the fuel mass is varying.
Yeah.
Can you explain your general strategy towards this? How do you deal with this?
Okay. You have some specific point where you need exactly the fuel aircraft to test it, as an extreme point. But in other cases, for instance, we had a procedure in our test aircraft that we can avoid to taking fuel from the wing, for instance, just the fuel from fuselage, and then test wet wing, all the points you can do. But this must be a test aircraft, which is a different procedure. And this is the main procedure I think you are following. You have, if you have just complete full aircraft to test, you only can do one test point, and then it's over. We also did this, but if you can plan it very well, that you can probably do half fuel testing after this, then you can do it, but in most cases you need special aircraft that you can switch on the pumps, that you have the right level of fuel.
Okay, thank you. Other question is regarding the safety factor to be employed when you are actually deciding on the flight envelope during or after flutter testing. The handbook recommends 3% damping or another criteria. In some cases, what our experience is, when we try to employ the 3% damping, we have to, cut down the envelope too much. It had to be too narrow. So we decided to relax on that, actually. But I'm wondering how you deal with this.
Okay, if you do clean aircraft testing, I think you should rely on the 3% damping criteria. This is important. Yeah.
Yes, ours was SLOR certification.
I know, yeah. So, but in a clean aircraft, please don't change the criteria of 3% damping, otherwise you run into some problems. There is a criteria that when you test external stores and the damping or the measurement on ground has shown that there is not much damping on it, you can also go flutter testing with 2%, yeah. But you have to track them, yeah. So you must have a good analysis, and you say, for instance, it never comes closer to 0. If you track it at 1.5 Hertz, then you can do it. This is allowed in this flutter criteria to do it, yeah. Only for external stores, but not for clean aircraft.
Thank you.
Sergei's questions are finished. Now we can start with others. Any other questions from Aselsan, Roketsan, and TAI, whatever? Yes, sir.
Elastic beam tunnel test. I want to ask a question about it.
Yeah.
Models. We can model the aircraft shape and we can model the aircraft stiffness. But how about the material and what about the building style of the parts? Can we, do they affect some penalties on model?
Okay, you can model the components, for instance, yeah, where you know exactly the material which goes into this model, and if it is a complicated structure and a difficult material, you do a ground test when you start from 0 to an airplane. You do a component test and you see exactly what happened. Because if you do a test, you know after this test exact what happened with this component, for instance. You get the frequency and the mode shapes, yeah? And then you can change some things like the bending mode or the mass properties that you get the right answer. So if you have an aircraft still flying and you say, I do some modeling and it doesn't work, you can't look for components, then you have to do a complete aircraft test and try to model it. Yeah. And an aircraft ground resonance test always gives you a good and solid information about the aircraft. Yeah.